step-by-step exam solutions. Okay, mathematics class, training you to excel. Subscribe to step-by-step exam solution. Like this video. Share the link of this video with others. Click for alert so that you receive the next video when released. Please drop your comment for a better service. Okay, math class, present 5 steps to exam success. Step 1, pray. Step 2, plan. Step 3, prepare. Step 4, preview. Step 5, performance. Okay, math class, present step-by-step exam solution to probability. In this video, we'll be looking at an introduction to probability. For the introduction to probability, we'll be looking at the following subtopics. Number 1, terms and definitions. Number 2, the axioms of probability. Number 3, experimental probabilities. Number 4, problems and solutions on probability. For this introduction, these are the topics we'll be looking at. The objective of our presentation are: number 1 objective, to name and define terms associated with probability. Number 2, to state the axioms of probability. Number 3, to solve problems on experimental probabilities. These are the things we'll be focusing on this particular presentation. Number 1, introduction to probability. Under this introduction, we'll be looking at number 1, definition of terms. The first term we want to look at is sample space. But before then, what is probability? Like I said, this session will provide a fundamental understanding of probability, exploring its basic concepts and application. At its core, probability is a measure of how likely an event is likely to occur. The likelihood of an event happening. So let's dive straight into the terms and definitions of these terms. Number 1 we'll be looking at is sample space. When we talk about sample space, the sample space is the set of all possible outcomes of a random experiment. The set of all possible outcomes of a random experiment. That is what we refer to as sample space. For example, if I'm to toss a die, what are the likely possibilities if I have a die to toss? On a die, I have 6 numbers, 1 to 6. So therefore, the possible outcome are or is a set of 1, 2, 3, 4, 5, and 6. So that's the sample space. A sample space with a countable number of elements is known as finite sample space. Finite means countable, something you can count. Now, another example of sample space is an infinite sample space. A sample space with an uncountable number of elements. That's an infinite sample space. That having looked at sample space, we are going to look at the next term, and that will be an event. What is an event? An event is any subset of the sample space. The sample space is like the universal set. Any other set that you can get from the sample space is a subset. It represents one or more outcomes that we're interested in. I told about the sample space of a tossing a die 1 to 6. What if I'm going to get an even numbers? Even numbers can be 2, 3, or 5. So they have a subset of the sample space. So now that's an event. An event is a subset of the sample space. It is the set of all successful outcomes of an experiment. Each outcome of an experiment is called an element, a member of the sample space. An element is a member of the sample space. So now, having seen that, then an event can be certain or an impossible event. Number one, impossible event. An event space E with no element is an impossible event. If there's no element, if it's not possible, it's an impossible event. For example, what would be the event space to get somebody that has 10 heads? That's an impossibility. So for such an impossible event, we will normally represent that by this symbol phi, meaning empty subset. Number two, we're going to look under this event is a certain event. When we talk about certain events, certainty means we are very sure that this event is going to take place. So when we are very sure, we say that the event is certain. Now, for example, if I toss a die, what's the possibility of getting 1 or 2 or 3 or 4 or 5 or 6 or 6? That's a certain event. Definitely will get one of them. But if I say I toss a die, what's the possibility of getting 20? Just one die. How can you get 20? It's an impossible event. Now let's look at example. Now, look at a fair die is tossed once. When we say a fair die, we are talking about a die that will deliver equal chances for each element, each member that is on its face, 1 to 6. What is the sample space? If I toss a die, what will be the sample space? Number two, what is the event space if the outcome of the experiment is a prime number? Yes, what will be the event space if we are getting a prime number? What if I'm getting a multiple of 2? What is the event space if the result of the experiment is a multiple of 2? Or let's say, what will be the event if it's a multiple of 2 or a prime number? Let's dive into the solution of this problem. We move to the next slide. Now we'll look at the solution. The first one, what is the sample space? Remember, sample space, a set of all possible outcomes. Now this is the all possible outcome if I toss a die. It can be 1, it can be 2, it can be 3, or 4, or 5, or 6. So all these are the possibilities. So therefore, the sample space represented by letter S, you are free to use any letter of your choice, would be elements that will be included in this set. 1, 2, 3, 4, 5. Then we close it. Remember, you must start with a core bracket and end with a core bracket. So that is the first answer to the first question, the sample space. Then number 2, what is the event space if the outcome of the experiment is a prime number? What do we refer to as prime numbers? A number that nothing divides except 1 or itself. So the first prime number is 2. The next is 3. Among all these 6 numbers we have here, the first prime number is 2. The next is 3. The next prime number here is 5. So we have 5. So now we have that. So therefore, the event space for prime numbers can be is 2, 3, and 5. We can also use P for prime number. We can use N for a number, so it doesn't matter. It's a matter of choice. Then the next question says, what is the event space if the result of the experiment is a multiple of 2? Multiple of 2, here you have 2, 4, and 6. 2, 4, and 6. So therefore, the multiple of 2, the event space will be 2, 4, and 6. So that gives us the solution to that first question. Very simple question indeed. But remember, we're moving from simple to complex. Then look at another example. Another example, example number 2, an unbiased coin. Unbiased means they have equal probability for any side of the coin to show up. There is no bias at all. It's flipped 2 times or twice. List the sample space. Number 2, list the event space if the result of the experiment is a head or tail. Now let's solve this question together. Let's look at the first one. There, if I toss, the first toss may be a head, then I have the head. It's also possible that the second toss will be a head, so the first and second will be head, head. It may also be possible that the first will be head and the second will be a tail. So you have head and tail. It also may be possible that the first will be a tail and the second will be a head. Then you have tail, head. Also, it may be possible that the 2 outcomes will be tail, tail. So now this gives us the sample space in picture. Head, 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 tail, head, and tail, tail. So therefore, the sample space for this experiment will be what you are seeing now: head, head for the first, head, tail for the second, tail, head for the third, and tail, tail for the last. That's the sample space. Now, number 2, we say list the event space if the result of the experiment is head or tail. So now, head or tail. Let's look at the ones where you have head or tail. The first one is this, head or tail. Look at it here, there, head or tail, or tail and head. So these are only 2 options. So the sample space will give us the first one, head, tail, or the tail, head. So that's the sample space. So now, for tossing a coin, there's something I want you to take note of. Please note this. Each flip is either head or tail, already explained by this diagram. The number of elements in the sample space will be 2 raised to power n. 2 because there are 2 options, head or tail. Power n. N gives us the number of trials. For this trial, for this one we have just discussed, there are only 2 trials, so n will be 2. 2 raised to power 2 will be 4. So therefore, you have 4 elements, 1, 2, 3, 4. So therefore, if I toss a coin twice, I have the number of outcomes or the number of sample space will be 4. What if I flip a coin 3 times? The number of outcomes will be what? 2 raised to power 3, 8. What if I flip it 4 times? It will be 2 raised to power 4, 16. 5 times, 2 raised to power 5, 32. And so on and so forth. So now we're going to move to the next slide for the continuation of this discussion on this topic. Now, definition of probability. Probability is defined as the likelihood, the possibility of an event taking place. Generally, we represent that as probability of the event, or let's say, yes, event A happening is the number of possibilities, the number of that event that are likely to occur over the number of the sample space, the number of all possibilities. The numerator here is the number of successful outcomes, what has happened, the outcome of the experiment. The denominator is the number of possible outcomes. We have already defined this as sample space and event space. That takes us to something very important about probability, and that takes us to the axioms of probability. The axioms of probability. What do we actually mean if I say axiom of probability? Axiom is a statement or proposition that is accepted as true without proof, often because it is self-evident and foundational to a system of thought. An axiom can also be the basic truth that everybody knows, or principle that doesn't need to be proven because it is what we already know. An axiom can be a starting point of reasoning or building a logical framework in mathematics. A triangle has three sides. It's an axiom. We don't need to prove that. We know that triangles have three sides. What are the axioms of probability? Things we cannot debate about probability. Number one, the probability PA of a certain event occurring is 1. When we are very sure that event will occur, that event will happen, the probability is 1. That is the probability of a certain event. Number 2, the probability of an event A is a positive number. It can never be negative. So if you are solving problem and you have the answer negative for probability, my friend, you are wrong. It's a positive number, and that positive number lies within the range 0 and 1. It will not be less than 0 and it will not be greater than 1. Certain event is 1. Uncertainty, event that we know that will not take place, is 0. So therefore, the probability of an event should be a number that lies between 0 and 1. And then we say 0 is less than the probability of that event happening, and that probability of event happening is less than or equal to 1. Number 3, the probability of event A written as P of A is equal to P. That is, if it will happen, we can represent that one that has happened, the truth about it is P. Then the complementary event, the one that has now have the other side, the opposite of it, is Q. Now, if I add P and Q, like if the probability of event happening is P, and the probability of that event not happening is Q, if I add them together, I'm going to get 1, because 1 is certainty. So therefore, the probability of a complementary event written this way, you can see it on the screen, is Q. And then if I add P and Q, I must get 1. So if I'm going to get 1, number 4, it means that the probability of a complementary event should be 1 minus the probability of that event happening, or Q is equal to 1 minus P. Please take note of these formulas. They are very essential for you to be able to solve problems of probability. You must not forget this. Then we move to experimental probability. Experimental probability. What do we actually mean by that? Experimental probability is the chance of an event happening based on actual results from an experiment or trial. It is not theory. It is not assumption. We actually carry out the experiment, and this is the result we are getting from the experiment. For example, if we say the number of cars that are parked at a particular garage, then we went there to number. Toyota is this number, Mercedes is this number, and then Peugeot is this number. These are experimental outcomes. If I toss a coin 20 times, I'm sure I will get a certain number of head and a certain number of tail. That is an experiment. If I toss a coin several times, I will get a certain number of either 1, 2, 3, 4, 5, or 6. That's an experiment. The outcome of this kind of experiment is known as experimental probability. Experimental probability just defined like other probability, the number of times that the event happens, which we can say the number of possible, the number of events, the number of successful outcomes, over the total number of trials, the total number of times the experiment was carried out, or you can say the number of possible outcomes. Suppose you flip a coin 100 times, and out of that 100 flipping, you got 48 heads. So now that is the result of the experiment. The number of heads in this experiment is 48. Therefore, the number of tails is 52. Then the experimental probability of getting a head should be 48 divided by the number of trials. And what's the number of trials in this experiment? 100. So therefore, I have the number of that, which is 48, over the number of possible outcomes, which is 100. So now, if that is the case, dividing that, I'm going to have 0.48. That is the experimental probability. Now, let's take more examples. The scores of 60 students in a midterm test in a certain school are shown in the table. 41 to 50, number of students 5. 51 to 60, the number of students 12, and down to 91 to 100. Question number 1. Find the probability that a student selected at random scored more than 70%. A student selected at random from that school must score above 70. Now, if the pass mark is 61%, how many students failed the test? This is the experimental probability because we are conducting an experiment based on the result of a certain subject in a certain school, and then we are seeing the outcome. Then let's now solve this together now. Now, number 1 says the number, find the probability that a student selected at random scored more than 70%. So let A be the number of students that scored more than 70%. So if that is the case, then we can now go to the table. More than 70 should be 71 to 80, 81 to 90, 91 to 100. You have 10 here, you have 6 here, and then you have 4 here. So therefore, the number of events A, those who score 70 and above, will be 10 plus 6 plus 4. And if you add everything, we're going to have 20. So now, then here, if the pass mark is 61%, then the number that fails should be the number that scored below 61, which is those who score from 41 to 60, 5 and 12. So now you have that. These are the ones that failed. So therefore, the number that failed will also give us that. So now, for the first one, finding the probability of a student selected at random scored above 70. So now we have the number of successful events is 20 as we have calculated, while the possible outcome will be addition of all these numbers we have here. We are told from the question there are 60, so you divide by 60. Then simplifying that, I'm going to get my answer as 1/3, or in decimal, I'll have 0.6667. The number 2, like we said, those that failed should be those that scored below 61. And that's 5 plus 12, giving us 17. So now we have 17. Please drop your comment for a better service. Then the probability of getting there, those that failed the test, would be the number of students that failed the test, 17, divided by the number of students that wrote the test, which is 60. So now 17/60 will give us 17/60 as the answer because we cannot simplify this. In decimal, we can write that as 0.2833. So now, another example. A fair coin is tossed 3 times. A fair coin is tossed 3 times. The first question says, what is the possible number of outcomes? Number B, list the sample space. Number C, calculate the probability of getting at most 2 heads. At most, highest 2 heads. Now let's solve this question together now. The first question says, what is the possible number of outcomes? a fair coin is tossed how many times? 3 times. Can you remember what we said? The number of sample space should be 2 raised to power n, where n is the number of trials. So how many times do we toss this coin? 3 times. So the number of trial n is 3. So we are going to replace n by 3. And 2 raised to power 3 will be what? 8. So therefore, we are expecting to have 8 elements in this sample space. We are expecting to get 8 elements in this sample space. So therefore, the total number of elements in the event space is 8. Now, the sample space is 8. Now, the next question is, list the sample space. Now, let's move to the next slide to list the sample space. Now, to list the sample space, we're going to know that if I toss the coin twice, we have done that before, the outcome will be head, 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 tail, tail, head, or tail, tail. So now to get for 3 times, I will now make a table. I place the first one here, the second one I place it here, the third one I place it here, the fourth one I place it here, and then I'm going to place the third flipping of the coin. If it's head, it will be here. If it's tail, it will be here. So if this is head, and then this two is already head, I'm going to have 3 heads. Then the same here, I'm going to have 2 heads and a tail. Now this coming to here, I'm going to have head and tail and head. Then I'm going to have tail, head, tail, tail. Now coming to this, that will be tail and then the head. Then this tail will come to this head, tail here. Then you're going to have tail, head, tail. This tail will come here. Then I'm going to have tail, head, tail. Then this one will come to this. I'm going to have tail, tail, head. And then this one will come to this. I'm now going to have tail, tail, tail. So now this is the sample space. Then we can now list them out the normal way. If you leave it like this, you are correct. Then that will give me that. So I'm just picking them and placing them in this core bracket. So that gives us the sample space, which already we are not already said that there will be 8 in number. Now, see question say, calculate the probability of getting at most 1 head. At most, that's maximum of 1 head. So let's check the places we have only 1 head. 1, 2, 3, 4, and then at most 1 head. At most, maximum of 1 head. It may be no head at all, but the head must not be greater than 1. So you have 1, 2, 3 of them here. So now we're not going to say the probability of getting a maximum of 1 head will give us the number of possibility of getting 1 head or no head at all divided by the number of sample space. And then from the table here, you can see there are only 4. I have 4 of them, and then over 8. Dividing that, I'm going to have 1 over 2 or 0.5. That's the probability of getting 1 head. Then the next question, the result of analysis of a certain school classified the performance of the students as distinction or credit. Out of 80 students, that's the total number of sample space that sat for the examination. The analysis of the results are summarized below. So that is the analysis. Now the questions follow. Now these are the questions. Now, with these questions now, we are going to move to the next slide to solve the question. Let's move to the next slide to solve this question now. So now, I have the table. Now those who had distinction, number of boys, 22. Number of girls, 18. If I add them, the total number of students with distinction then would be 18 plus 22 will be 38. So now, for those who had credit, and there are only 22 girls with credit, and 30 boys with credit, and since the question is asking for the number of girls with credit, so now we now know what to do. So now we're going to answer the first question. The number of students with distinction will give us the number of distinction, 22 plus 16, divided by the total number of students we have in this particular school. So now That's the number of sample space. The number of distinction, adding this is 38. Then adding all the number of boys and girls we have in that school will give us 80, and it's already given in the question. Now simplifying that, we're going to have our answer as 19/40, which you can write also in decimal as 0.475. Then the next question says, so the number of girls with credits. So the number of girls with credits. So you have that. So the number of girls there is 22 divided by the total number of students, 80. Simplifying, I'm going to have 11/40. In decimal, I'm going to have 0.275. That brings us to the end of this presentation. Remember to subscribe, like the video, share the link of this video with others. Click for alert so that you receive the next presentation. Thank you for watching.